So that's all I have, and I don't know if we're doing questions now.
Thank you very much, Chris, for that excellent presentation. Some of you who are not structural engineers might have been a bit baffled by some of the response spectrum and so on, but I hope the visual effects that he showed would illustrate what he was trying to do. Right? Before we go on to the final presentation, I would like to apologize for not recognizing your proper name, because I was sitting yesterday between the two Chris's, and I think we should invite the two co-authors to stand so that there were three of them who wrote this paper, but they decided that Engineer Braden would be the one to present. But the two other engineers who, I think they all work with Hallcrow. Some of you would know the firm of Hallcrow, who they were bought out by CH2M. Right? In fact, only yesterday, just since we have some time, I'll tell you all this. I was talking to one of the other co-authors, Billy, because he is based in London with Hallcrow. And we were chatting, and I asked him, because one of my ex-students, Maurice Allgrove, some of you might know of him, from Jamaica, was actually interviewed by Billy for a job at Hallcrow. It's a real small world that we live in. And I would like to invite Billy to stand up so that you know the other two authors. Billy with Hallcrow H2M, and the other author is Chris Ray, the other Chris. That's who I thought it was. Right? So, and a bit of information, they are the designers of all the bridges on the Sir Solomon Hochoy extension that is currently being built by OS, the Brazilian firm. Right? And in fact, some of you who have used the extension, you might have seen the first steel plate girder bridge that has been built, designed by them. Right? Some of you might have seen the bridge on the first part of the extension. Okay? So having said that, I'd now like to introduce the third presentation in the person of another Hallcrow man, which will be presented by Engineer Edward Albada. Edward has over 15 years experience in a wide range of coastal engineering and project management roles of coastal and marine projects. A professional civil engineer in both the United States and Trinidad and Tobago, Edward specializes in coastal modeling, including wave and current forcing simulations, storm surge simulations, port and marina design, and flushing analysis, and coastal design and construction-related experience in numerous shoreline stabilization schemes. In addition to his technical role, Edward serves as country manager for Hallcrow CH2M Hill and oversees multidisciplinary operations in Trinidad and Tobago and the Lower Caribbean. So Edward comes to us with a lot of experience, and I would now like to invite him to the podium to present his paper, Design Evolution for a Proposed Port Subjected to Earthquake, Hurricanes, and a Volcano at Cars Bay, Montserrat. Some of you know that the capital, Montserrat, Plymouth, was completely destroyed by the eruption of the volcano, and the new city had to be built to the north at Cars Bay. So I'd like to invite Edward Albada to come to the podium. Thank you.
Okay, my name is Edward Albada. I'm a coastal engineer with Hallcrow CH2M Hill, and apologies also, we keep calling ourselves by two company names, but we're going to make a decision and settle on one name probably this year. So my presentation today is the evolution of design for a proposed port in Montserrat. I will be I'll be talking about Montserrat, introducing Montserrat, describing the need for the project constraints that we've encountered during the development of design, the outlined design evolution, specifics on design for the very arduous hurricane conditions that are experienced within Montserrat, and conclude with maybe a brief summary. So Montserrat is in the Leeward Islands. It's just adjacent to Antigua, and pretty much right in the path of where most hurricanes seem to pass in the Caribbean. Fortunately for us, we're below that hurricane belt, as you all know. It's a British overseas territory, approximately 16 by 11 kilometers. Population, at one point, Montserrat had a population of about 15,000, but following the eruption of the volcano, there was a lot of evacuations, and well, quite simply, the people didn't ever return. This project is intended to be a stimulus for people to return to Montserrat. The economy presently is effectively stagnated following the eruption of the volcano. It used to be a lot of tourism, a lot of high-end resorts, and so on and so forth. Very meager annual budget being sustained by the UK government. The only industry effectively is some small-scale sand and aggregate that some entrepreneurs are taking advantage of the abundance of what they have now, which is volcanic sand. It's very good quality sand, by the way. So there's very little going on in Montserrat. So Montserrat really got decimated first by Hurricane Hugo in 1989. Sustained winds were approximately 140 miles an hour and created widespread damage throughout Montserrat. And they were right on the road to recovery from that hurricane event when they had a big volcano blow up in their backyard, the Soufriere Hills volcano eruption. 2/3 of the population were evacuated, and the capital, Plymouth, was completely buried. The airport, as well as the port, completely buried. And I had the honor of actually walking through the capital as it is now, where I took these pictures. These are pretty amazing. There are buildings up to 2-3 stories high, which are now covered over in this volcanic ash and volcanic sand. And this is the port, the old port in Plymouth. The jetty, the pier that served as the port in Plymouth. It's now completely covered up, accretion by the volcanic sand and dust. And although this picture doesn't show it, about 50 meters to the left of this picture used to be the shoreline. So if you go there, you'll see these shoreline stabilization units, and they're sitting on dry land, which is quite bizarre. Presently, the entire southern half of the island is declared an exclusion zone because of the ongoing eruptions from the volcano, and then there are some caution zones that you're not allowed to visit during certain times or when the volcano is active, especially active. So following the eruption of the volcano, an emergency jetty was built in Little Bay in the safe half of the island. That is the jetty. It's about 80 meters long. It's in a small area called Little Bay, and it was initially built for evacuation. So it was constructed quickly just to get people to safely off the island. Since then, the jetty has evolved into sort of a semi-functioning port, I should say. It unfortunately is undersized for their needs, especially considering the pending development. There is completely exposed, and in particular there is the occurrence of north swells in the Caribbean between November and April, and even small little north swell events completely close the port. This is a swell event that I witnessed, and that structure is completely buried right now. You can't even see it in whitewater. I was also there during an offloading event of one of their containers where it was essentially flat, calm waters, and there must have been a slight swell in the water. And they were swinging this container back and forth. It was banging against the ship, and 2 people got injured. So it's a safety issue as well as an operational issue. Little Bay, there's grand plans for Little Bay. They want to do they want to regenerate the capital city in Little Bay. And so a port is needed for shipment of construction goods and services and so on and so forth. The existing port is completely undersized for what they are planning to do. So some of the constraints that we experienced in the design, the client had specified as a 50-year design life as well as a 50-year return period storm event. So that's essentially a hurricane condition. As with the rest of the Caribbean, it's in a seismic zone, and this is the seismic criteria agreed for use. They wanted a multi-purpose facility, so they wanted one port facility that serves the entire, all of their needs in Montserrat, which I'll go into a little detail. That was the trickiest part of the design so far. It will be funded by external agencies. We're not too sure who's going to fund it yet, but it's quite likely that the UK government and the EU are going to divide the funding. And of course, they are looking after their financial interests. They wanted something as cost-effective as possible. We want to solve the downtime constraints experienced at the existing port. Montserrat's a small island. It's got limited natural resources, limited skill. Well, at one point I had skilled labor force, but there's limited labor force, and so skilled or unskilled. There's only one hotel there, so very, very little supportive industry. There's, of course, a requirement to maximize the local materials, even though they don't have much. There's a requirement for interdependency between the functionality of the port and the new town center, the vision for the new town center. And they are really looking at cruise passengers as a major industry, and quite rightly so. I mean, Montserrat can offer a lot for the cruise passenger. They have an active volcano. They have a town that's buried in volcanic ash and dirt and dust and so on. So there's a lot for the cruise passenger to see in Montserrat. There's very limited land for construction staging. There's, of course, the environmental considerations. This part of the island, there's a lot of beautiful coral reefs, so we're trying to minimize the impact of that. It's in the airport flight path, and of course it needs to be ISPS compliant. That's the International Port Security Code. These are the vessels. I said that they wanted a multi-purpose facility. So these are the vessels that they're looking at to accommodate within the port facility. The market analysis for the type of, or the size of the cruise vessel showed that in this part of the Caribbean, the minimum recommended cruise vessel length is 294 meters, which is easily the most arduous requirement for our design. In addition to that, there's the cargo vessels of 130 meters and about 10-meter draft, a fuel vessel that calls presently in Montserrat at 112 meters, ferry and ro-ro about 50 meters. We have to also accommodate for fishermen, recreational vessels, and finally they threw in, we also want mega yachts as well. So All of this in this small port facility. This is the master plan that, actually it's an old version of the master plan. It's evolved significantly after that, but this shows that the intent of the developers and the government of Montserrat for what they want to see in their new capital city. I'm not going to go into too much detail, but this was the master planner's concept of where the port should go and their initial layouts. The problem is, right here is earmarked for development. This is called Potato Hill, which is this area right there in the picture. And there's another hill over here called Gun Hill, which is right over there. And the port facility had to fit in between there. Now, I mentioned that we had to accommodate a 294-meter vessel. And the distance between Potato Hill and Gun Hill is 300 meters. So we had to kind of squeeze it in the two hills. So I'm going to briefly go through some of the initial concepts that we came up with and how they evolved over time. And I'll just go through them quite quickly. These were the initial concepts we developed in day one, and they were shut down because there's too much reclamation and oops. Sorry, too much reclamation, and this was the Potato Hill area, so we had to move everything this way. This is when we pushed the development further south to accommodate, to not interfere with the Potato Hill development. We did some more changes to conform to the ISPS code. In particular, you want to separate the international activities of the port with the domestic. Domestic being the fishing facilities, the marina area, and so on and so forth. We were then told that, that the port that we were trying to develop was way too expensive, so we had to cut back, and we did so by reducing the reclamation areas and looking at some alternate concepts that would be more cost-effective. We then added provision for a marina in 3 concepts, and we had an increase in the cruise berth. Now, while these concepts were being developed, the other activities and reports and studies were being analyzed. So it was very much a parallel task process. So the evolution the design had to evolve when more and more information came in. So this is an example. This is when we started getting the cruise analysis coming in. And initially we had developed a 200-meter cruise vessel. And it slowly increased over time as more and more information came in. These are the phase 1 concepts that we developed. And option 2 was chosen as a preferred layout. We did further refinement to option 2. We did some value engineering. Let me just pause here and describe some of these areas. We have an offshore breakwater out here. We have one berthing facility that serves both as the cruise and cargo. This would be the Ro-Ro area, the ferry terminal, and the marina. When we started looking at the impact of there's a river that comes down here, which I'll discuss in later slides. We looked at the river impact coming and discharge coming right adjacent to the port facility, as well as there was an updated need for a larger marina. We had to consider taking down Gun Hill. So this is a picture of Gun Hill down here. And we had to develop a grading plan to essentially grade Gun Hill to shift the main port into where Gun Hill is now and expand the area for the marina. And in addition, we had to reroute. This is Collins River. Collins River now comes out and discharges to the south. So we did a grading plan for Gun Hill, and actually that's the first phase of the development. That Gun Hill is now been graded. It's gone. We added some mega-yacht facilities where we could fit them. And at this point in March, April 2013, we had maintained the need for a two-entrance port, an offshore breakwater, in which vessels could come and access the berth, and then, if needed, they could leave through the north entrance. And we did that for a couple of reasons, one of them being a safety issue, and the other one, so if the vessels get into trouble, they have two ways of getting out. But we had been doing some navigation simulations in the Star Center in Miami, where they go and simulate. They have a professional pilot, and they go and actually do but navigation simulations in a real-time environment. And this is one of the results of that navigation simulation of a cruise vessel entering the port and leaving through the north entrance. And the ship captains, they didn't like this north entrance at all. They thought that it would never be used. So we had to rethink the need for an offshore breakwater. And we came up with a closed breakwater system in which the advantages of this is now you can construct the breakwater from land, whereas before you would have to construct it from barges. So this significantly cut down a lot of the expenses. So basically, made a lot of people happy. We cut the costs down a lot. So this is basically where we are now at 90% design. Looks like. Well, this is another image. So this is our responsibility in the project. It's a breakwater, a facility for the marina, the port, and some changes to the riverine outflow. The marina itself, with all of the finger piers and so on, will be handled by others. And this will be the town center development that will also be handled by others. Okay, for the next half of my presentation, I'll be discussing some of the considerations that we've had to look at specifically for the hurricane design criteria that we're mandated to design to. So, as I said, there's a river that runs right along here and exits right north. This is Gun Hill, which is now graded. And like most places in the Caribbean, there's several infrastructure that has been put on the floodplain of that river. It was unwise planning and unregulated planning, and this isn't only private infrastructure. Right here, where you're seeing these buildings here, this is the tank farm for Government of Montserrat. So these tank farms, which are diesel, LPG, and so on and so forth, serve the entire island, and it's essentially an infrastructure that can't move. So here we have the river coming out here. We have infrastructure within the floodplain. Everything is directed under this road here, and this is the Collins River Bridge, which is also undersized. And presently, during a severe rainfall event, it doesn't have to be a tropical storm or hurricane event, the road is overtopped. So all of these we had to address in our design, because if we don't address it, then all of the water ends up in our port. So these are some of the constraints. Or the other thing we had to look at is and I don't think anyone could see this very well, but there's a lot of sedimentation of this volcanic sand and dust that comes out of these rivers and channels, and it leads to a lot of shoaling. So we wanted to try and ensure that the new port could be as maintenance-free as possible. This Collins River has quite a large catchment area considering the size of Montserrat. It extends all the way up to Silver Hills. So it extends from 0 to 650 meters, 20 kilometers in length of stream. We developed the hydrograph from limited data from Montserrat and used also data from Antigua. We addressed the effect of climate change using the UNDP climate change country profiles and ran 2 different types of models. And this is a map of the inundation as it is presently for I believe this is a 50-year storm event. So the area in orange shows where the flooding occurs on a 50-year storm event. And it easily defines where the floodplain is within the Collins River area. There's also another river over here. There's some drainage channels over here. But we're more at least for the purposes of this presentation, I'm only going to focus on this area. Following a opening of a bridge, a widening of a bridge, and a channelization, at least downstream from the bridge, the area in green demonstrates the flooding potential. So we've solved the issue of the overtopping of the roadway, and we've managed to contain the flooding away from the port area. But there's very little that can be done at this stage, given the 50-year storm event, to stop the inundation of the infrastructure. And in particular, the government of Montserrat wanted a solution to the flooding in their tank farm area. This is an ongoing design, so we still have between 90 and 100%. So we've been tasked to come up with further infrastructure works to try and stop the flooding in the tank farm area. We also had to look at sedimentation. So what we did was we designed 2 sediment traps to collect some of the larger boulders and gravel-sized pieces. We looked at this was an iterative part of our design, but we looked at the plume dispersion as the sediment comes out of the rivers and where would it end up. And this is the existing, the port is actually here. It's kind of hard to see. This is the existing condition, and the plume essentially heads to the north and would head straight into our port facility. With the redirection and rechannelization of the river, it now is directed to the south, away from the new port basin. And this is an animation of a dispersion within the port basin. It's used for 2 purposes. One, to demonstrate compliance for the flushing potential in case of a pollution spill within the basin, and also to calculate and assess the potential for sedimentation. With the closed breakwater system, unfortunately, it's now created more of a more stagnant basin, and then the effect is there will have to be more maintenance dredging required. So we've disclosed this to the client, and they're incorporated into their annual maintenance budget. I'll now switch to more the coastal design, and this is the area of the design of the breakwater and the quay walls. The initial stages to the coastal design, we did a detailed literature review. We looked at 75 years of hourly data from hindcasted data, which encompassed 285 storm events. So we think we have a good grasp of what has happened in the last 75 to 100 years. We also appended that with additional data from the WaveWatch 3 hindcast models. We also collected data. We collected ATC data, which is currents, waves, and tides, essentially. And those we use in the calibration of our numerical models in the coastal design. Using the hindcast data, we did an extreme value analysis using the point over threshold method for wind surges and as well as sea level rise. Well, the sea level rise, we used the modified NRC2 scenario for the climate change and came up with expected sea level rise of about 0.5 meter in 50 years. In addition to that, we used we did our own dynamic hurricane simulations. So, well, essentially what this does is we gather the data from past hurricanes and input the wind field into our numerical models and essentially simulate the hurricane, passage of the hurricane, and extract from that wave heights as well as surges along our area of interest. And our area of interest right here, of course, is Cards B. And this animation is the surge height. It's the surge height of the passage of Hurricane Luis. And as you see, could have had another animation showing the actual wind field, but yeah, maybe I'll do that for next time. So you can see that the surge comes in as a hurricane passes Montserrat, and then eventually it is dissipated. We did that for a series of hurricanes: Hugo, Jose, George, and Lenny. And this is really a check on our extreme value analysis that we use from the hindcast data. So this is ground truthing to ensure that we had the right estimates for waves and surges. Using all of that, we extracted wave heights along the boundary of the breakwater. I'm concentrating on the breakwater design here because that breakwater is, all in all, it's 700 meters of breakwater that's required. And it's easily the most expensive, individual most expensive item on from the entire design. It's approximately 50% of the budget, of the expected budget for construction. And the 50-year hurricane return period shows a wave height of approximately 7 meters. And this breakwater is in approximately 12-meter water depth, so quite severe conditions for design. So using the information from the numerical models, we came up with a breakwater design. Actually, we came up with 2 breakwater designs, which I'll go into a little more detail. For those who know about coastal structure design, the most common type of material to use is rock. Unfortunately, for 7-meter wave heights, you have to use concrete army units. So for this, we selected core locks, and we're using 9 to 11 cubic meter units. Approximately 4,700 units would be required. Now, what we did, I said we came up with 2 designs for the breakwater. We wanted to try and maximize the use of local materials, so the only thing Montserrat has in abundance is sand. So instead of a traditional core breakwater, which is more rock material, we suggested the use of these geofabric tubes to either use the sand from the volcanic sand or the sand from the dredging, pump it in, and use that as the core. Now, given the conditions on site, we recommended to the client that, is that binging because I'm out of time? I apologize. I'm almost finished. I'll run through the next ones quickly. Okay, so the breakwater design, we recommended they do a 2D model test, and we did that in a laboratory in South Africa. And this was some images of the setup of the model. This is the geofabric tube breakwater, and then they do the underlayer and then the concrete army units to scale They color code it, they instrument it, and then they hit it with the 100-year or the 50-year storm event. So now keep in mind that the master planner wanted a very low crested breakwater because he wanted to see over the breakwater. So that was another very difficult and challenging design criteria. So the crest of the breakwater is plus 4 meters, and we have a 7-meter high hurricane wave hitting that. So coming out of the 2D model study, only one change was needed. But in the end, we had to discount the use of the geotube breakwater design. The seismic design drove it up, and nobody would warranty. Neither the manufacturers, the contractors didn't like it. They thought it was too difficult to construct. So we did away with this design in the end. I won't go into this given I'm out of time, but we also developed a concrete block structure for the quay instead of the more traditional and less expensive piled foundation. And this is what the concrete blocks look like. This is a project in Abu Dhabi. So I'll just summarize quickly here. The natural disaster events really defined the design criteria that was adopted in our design development. The other summary I have is port development for 300-meter cruise vessels is very challenging and also very expensive. I would like to acknowledge those, many of them are in the room today that supported us on the design. Geotech Associates did the geotechnical site investigations, Eco-Engineering, the environmental, coastal dynamics, Met-Ocean, and a lot of the design, it was a global, we used all of our design centers to develop the design, but a lot of it was done locally, as mentioned here. So apologies for going over time, but I can entertain any questions. So.